All right, cool. So it seems like this test is over a lot, but every chapter is just like a couple sections in there, right? But we start off back in chapter 4. Yeah, cool. And that's where we did the XP of X stuff, right? So you've got the mean. It's this guy. Of course. So this is all stuff that could be on your formula sheet. The beautiful thing about the formulas is they tell you when to use them. You use them when I give you an X and a P of X. Shoot, right? That column stuff. I like it. And then I think it might be easier. It's up to you. You can either write the variance, or you can write standard deviation equals the square root of all that. Either way you want to write it. You guys with me? Because if you get the variance, how do you get the standard deviation? You take the square root of it. Okay. So that's for just general probability distributions, where they give you all the values and they give you all the probabilities. Right? So a more specific probability distribution we looked at was a binomial probability distribution, and that's what I call an NPQ problem. Because you can identify a probability of success, a probability of failure, and then a number of people or things or trials. Like it. So they kind of jump out at you. 17% of people enjoy, I don't know, something. So it must mean that 83% of people don't. So there's your P and your Q. And I say I pick 50 people. There's your N. There's an NPQ problem. I'm going to use these formulas here, right? The standard deviation was, who remembers?
Square root of NPQ.
I love it. And the probability formula for this was that N choose X, P v X, Q v N minus X. I need to see this, both in your homework and on the test. If you just write binomial PDF, no, that's not work. You're telling me what somebody else did, namely your calculator. So don't tell me, oh yeah, my calculator did this. Well, that's nice for that thing. Now, I will say in the homework, there's a few evil questions where you should use binomial CDF because they don't want you to do the formula 20 times. It's insane. I'm not going to give you that kind of problem, right? All right, how are we doing so far? Right? So this is all from chapter 4. Okay, cool. Let's see, then chapter 5. Let me make sure I didn't miss anybody. No. Good Lord. And chapter 4. Oh, yeah. So chapter 5 is where we first got into continuous variables, right? So this is for discrete variables. So X would be 0, 1, 2, 3. This could only have 4 people liked it, 5 people liked it. You can't say 3.5 people liked it. That's weird. Right? So these are discrete distributions. And then we got into continuous distribution. We have uniform distribution. I'm not even going to write the formulas down. I think I told you this when I first said, I just wanted you to realize there are formulas. I'm not going to give you a uniform where you have to find the mean and the standard deviation, that weird square root of thing over 12, right? I wanted you to use in the homework just to know that they exist. I'm not even going to put it on the test. Right? It's not really used that often, to be honest. So that's, I'm not going to put it down. And then, of course, we got into normal distributions eventually. Blah, 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 blah. Yep. So that's chapter 6. And this is where we have this formula, of course, one of the most important ones. Right. Let's see. Oh, we have the reverse of that guy. All right, just solving for X. I desperately want this to make sense. What's one question you know is going to be on this test? That I've already told you is going to be on this test. What does the z-score tell you? And this formula says, what does the z-score tell you? It tells you the number of these, the number of standard deviations away from the mean to the data point. I mean, you can read that math formula in English, right? You can actually do that more often than you realize. Okay, maybe, I don't know. So you can't have notes on your formula sheet, but you can have formulas, and oh, that's a note. Oh, well, Jeff, too bad. It's a loophole in your little rule. If you realize that's a note, you should not miss that question. So everybody get that question right. We all know the answer to that question. Please. Let's see, what else? Blah, blah, blah. Oh, so this is your standard z-score problem. What happens when I take a sample and I ask about sample means? What has to happen? Oh, shit.
You divide the standard deviation.
It's been a while, I know.
Square root.
Yeah. So this sigma is good for individuals, right? That tells me how spread out individuals are from their mean. If I take a group of 20 and I say what's the probability that the sample mean of those 20 do something, I have to compare them to all the other groups of 20. I need the standard deviation that works for a group of 20. That's not what this guy does. So I got to create the standard deviation that works for means is the individual standard deviation divided by the square root of my sample size. So if I had a group of 30, I would take this standard deviation divided by the square root of 30. That's now the standard deviation for a group of 30. And that was the whole thing about going to Florida and taking all the people and their ages and stuff. The more people I take, the skinnier the picture should have gotten. Because the bigger your sample, the closer and closer it should be to the real average. Right? That only makes sense. Please let it make sense. So I can take an individual person and have them be 7 foot tall and not freak out too much. I figure maybe 7 foot tall might be a little too much, but if you had one person come in the room and they were 7 foot tall, you go, oh. If you had 20 people randomly just walk by and they had an average of 7 feet, that would be something to stop and watch, right? What is happening over there? You agree? You understand? So that means groups of 20 should be closer. That's why the picture gets skinnier and skinnier. That's why the standard deviation gets smaller and smaller and smaller the bigger the sample you take. 50 people walking by, average of 7, that's like, okay, everybody stop. We got to go there and see what the hell is happening. Something is happening, right? Or not. You guys, I would go, what the hell? I'm going to go watch it. You guys stay here and do a stats. I'm going to go see what the hell's happening with these 7 foot tall people. All right, maybe. Okay, all right, sorry. All right. Let's see, anything else? I think that's everybody. Yeah. Anybody have a suggestion for a formula that I missed? Is there any formulas that I missed? I like it. You're like, you got me, buddy. I feel like it's the first day of class right now. Okay. So that's your formula sheet. That's what can be on your formula sheet right there. You could bring in the old formula sheets you got, as long as there's not ones that you lost points on. Each time you take a test, you can just keep bringing in the old formula sheets along with the new. So for the final, you'll have a little stack of formula sheets. Beautiful. I love it. Kick ass. As long as they're all legal, you're okay. Okay, now, if that's all the formula stuff we're going to talk about, I can, whatever you guys want to talk about, just wide open, yeah.
I can't seem to remember how to get to the MCX, PX on the calculator.
Oh, all right. It's like, how long is that show going to go on? All right. That's true. All right, so. All right, let's do a problem. I need to hire somebody. All right. So everybody got what they need from here? Okay. So now the stuff I'm writing cannot go on your formula sheet. So let's do an example of a binomial situation. All right, so let's say 17% of all stat students enjoy talking about central limit theorem. All right, stats cult, CLT. So, and then I say we take a random sample of how many, Jeff? Let's say 58 stat students. All right. 1. What's the probability that more than what, Jeff? I don't know, Jeff, man. More than 11 enjoy talking about central limit theorem. Let's not do that. Let's say exactly 11. Sorry, I'm just going against what I said earlier. So real quick, what's N? What's P? What's Q?
N is 58.
N is 58.
P is 0.17.
0.17.
And Q is 0.83.
Cool, I like it. So for some reason, don't leave 17% as 17. When you put it in this form, in the formula, it's 17 to the crazy power, and you're going to get huge numbers, and you're going to go, I don't know math. It's because you put the wrong stuff in. 17% is 0.17. Percentages are stuff that humans made up. I know we made numbers up too, but 0.17 is the actual number. 17% is an idea. So make them into decimals, right? And how did you get 0.83? Where'd that come from? Must be everybody else, right? I like it. And then, so how do I set this up? The formula is n choose x, p to the x, q to the n minus x.
58 choose.
Yeah, so I got 58 students. I want to choose
11.
11 of them to do this.
7.17 to the 11.
So I got 11 that do this. So how many do the other thing?
0.83 to the 47.
Good, the rest of them. 47, because what do these two always have to do? Add to be total number of people, because you got to do one thing or the other, because they're opposites, right? You can't say, I don't do either one. No, what do you say, what? You're alive or you're dead? No, I'm in the middle. No, go away. Walking Dead, I don't know. They're walking dead. They're still dead. There you go. End of discussion. But they're walking, but they're dead, sure. All right, so how does this get put into the calculator? That's the real question, but I had to give a little context as to where a formula would come from. Let's see what this thing looks like in the calculator. Woo-ha. Ooh, the game driver is ready. So I got 58. Where's my choose? Where's the...
It's in math.
Yeah, go to math.
PRB.
Herb. Liquor. So NCR number 3, not number 2, not National Public Radio. So 58, choose 11 times.
0.17.
Yeah, 17, I got 11, 17%, so I must have, so times 0.83 to the 47. So that, 12.27% or 12.3%. How are we doing so far? Is that decent? So that obviously answers the question. You just got to remember, come test day, how to get there. And if you forgot something like that, just come up and ask me. Normally you're pretty close. You're just not confident about it. Yeah?
As far as on the test, like writing that out, would it be okay to just put the decimal, or do you want to...
You write this out, and then...
the actual answers.
Yeah. So either way. So if you put 0.1227, is that?
Okay.
Or you can put... Okay, you're dead. You can put... there's your 12.27%. If I remember, I want to put on there, just like I did on that one probability quiz, round all decimals to 4 places or something.
But you want to see the equation written out.
Totally. This is your work. This is your work. Please, dear God, if you do any of these individually, they might actually overflow or something, right? This could overflow, but then these are so small, they bring it back down. The calculator's cool with it. The algorithm it uses kind of balances it out. So don't do any of these separately. Do the whole damn thing at once. Otherwise, you're going to get monster big and monster small, and you're like, how do I write that? No, screw that. Just do the whole thing. You guys okay with that? So your work is setting the equation up. And then your answer is just the decimal you get, or you can make it to percentage. I like it. Okay. All right. Okay. Oh, let's add on to this something. What's the mean expected out of 58? What's the formula for the mean?
N times P.
Yeah, the mean is NP. So the mean in this case will be
58 times
0.17. Is that cool? You gotta love that formula compared to other ways of getting means. You don't have to, but you should. So what is that? 9.86? So now you see why I picked 11, right? It was close to the mean. If they get too far away from the mean, the probability gets so small that this sometimes gets a little weird to read. If you saw this on your calculator, 3e negative 11, what would that mean? So yeah, it's 10 zeros in front of 11. It's times 10 to the negative 11. So you got to move the decimal back, so it would be 10 zeros, 3. Basically, humans would call that about 0% chance. It ain't happening. Yeah.
Could you find the mean first and then like round and then use that in your formula? Like you said, you chose 11, so that was good because it was close to the mean.
Oh yeah, I just estimated the mean and picked a number close to that estimate. That's all I did to get 11. Does that make sense?
Yeah.
Because if I picked just 28, then I would have gotten something weird. I didn't want to get it too weird. I like it. All right. And then what's the standard deviation?
square root and PR, or NPQ, excuse me.
That's right. So square root 58.17, 0.83. 2 point something, yeah. So that's before you took a square root? I'm sorry, do it.
Yeah, sorry.
8607.
2.861. All right, cool. All right, so this is the kind of problem I would give you. This is exactly the kind of problem. Give you a situation, and then ask you probability questions, and then ask you mean. And what do you think would be the next question? Have we done this enough? We just did that?
Wait. Unusual?
Yes, cool. Look at that. So would it be unusual to find, what, Jeff? I don't know, Jeff, man. It would be unusual to get 17? Be unusual? I love my grammar. Would it be unusual to get 17? Would 17 be unusual? If I had a sample of 58 stat students and I got 17 that enjoy talking about the central limit theorem, they'd probably just suck ups. But if they're really being honest, would that be unusual? Well, how do you figure that out? Where's unusual start? Where's unusual start? How far away from the mean you gotta get? Yeah, so you go 2 standard deviations up, 2 standard deviations down. Some guys might realize I just gotta go up, which is fine. Some of you guys did that on that last quiz. I think it was the last quiz. Beautiful. Why would you go down when it's 17? So if you go up 2 of these, so do 9.86 plus twice this, where do you end up? Yeah, 15.582. Is everybody able to get that number? Does everybody see where that number came from? Okay, it's on you to speak up, so I'm going to, okay, good. So would 17 be unusual then? Yeah, because I really want this to make sense. Just like there's an average height, and if I go 2 standard deviations outside of there's unusual. So there's a certain height somebody could hit where you would go, what? Because you're not used to seeing that every day. If I saw somebody 3 foot tall walking down the sidewalk, I'm not being rude, I'm just being biologically human. I'm just going, oh, I don't see that all the time. That's interesting. Are you guys kind of with me? Right? You don't see that every day. So you try not to be rude, but you're going to do that because it's normal. It's an unusual thing, so we naturally look at it and do a double take. Are you guys, that's what unusual means. So I expect it to be close to the average, so if it's far away from the average, how do we define far away right now? 2 standard deviations more than that. Later in the course, we'll make that a little more specific. But right now, about 2 is good. So if it's more, and it is more than 2 standard deviations away, that's unusual. That would be a little weird.
So on the practice test, you had a question, find the minimum maximum values.
Yes.
0 and 58?
Yeah, in this case,
Or is it going to be...
what's the, if I said max and min values, then what's the maximum expected would be this? And the minimum is 9.86 minus 2 of these, right? Go down 2.
You didn't say expected, you just said find the minimum and maximum values.
All right, sorry, that's my bad. Should be expected values. Expected values. My bad.
Okay.
Yeah. Yeah.
Just checking real quick, so you added 2 standard deviations to get 15.582.
Yeah, you take 9.86 plus 2 of these.
And because 17 is greater than 15.582.
Yeah, 17 is out there.
It is
Unusual.
Okay.
Exactly. It's the same thing as seeing somebody who's 7'7" tall, 7'7" inches tall. Is that unusual? Yes, because they're so far away from the average. They're more than 2 centimeters away from the average. Yes.
So it's always going to be 2 standard deviations from the mean, unless you tell us within 1.
Yeah. So sometimes I have a question about what percentage is within 1 standard deviation, and the reason I do that is for most of the XP of X stuff I make, if you go 2 standard deviations out, you can catch all of them. It's just because it's not that big of a thing. If you go 2, and so I wanted to make it more interesting, so I just go 1 step out. What percentage do you catch? Unusual starts 2 steps out. That's the way we're defining it right now. When we get up into something called hypothesis tests and stuff like that, we're going to define that better. Because your unusual might be different than somebody else's unusual, right?
Yeah.
So we have to be able to refine that too. We got to make it different for different situations. But right now it's just 2. I like it. All right. So while there's a lull, there is one idea related to number 5.2b. Right? It's like, what the hell's that? So, and this is related to, yes, right? Which problems was it? 85, 86?
Yeah.
Okay. So in chapter 7.3, number 85 and 86, they both relate to something called the normal approximation to the binomial distribution. My God. So I was desperately hoping I'd have time to put that in, but obviously we didn't. And I forgot I assigned some homework for it because I think I was more optimistic at the beginning of the semester. So if you've hit number 85 and 86 and 7.3, and you're like, what the hell? That was a good reaction because we didn't talk about them. I do want to talk about one thing, though. The most important thing out of that section, because we sort of, as stats teachers, we sort of stopped teaching this because technology is able to do this better. But do you remember that handout and we flipped a coin 14 times so that there was an average of 7 heads? It was the tallest bar. And doesn't this, how would you describe this picture to me? It looks roughly normal, doesn't it? I like it. Why does it look normal? Well, to get kind of less technical, it starts low, it goes high, it goes low. Right? All right. Is that cool? All right. So, and the mean was 7 because I flipped the coin 14 times, and the probability was 0.5, so the mean was 7. How do we know so far? Okay, so, for a binomial situation, this is going to be an interesting question. Stay with me. What's the smallest value in a binomial distribution? What's the smallest x value? So again, what's a binomial distribution? You got 20 people, and 70% of people like Game of Thrones. All right, so what's the smallest number that could like Game of Thrones? 0. It's always 0. You with me? Always 0, because that's the least you can't have negative people. That's a little freaky. That's like antimatter people. I don't know what that is. And then the most would be all of them. 0 up to whatever. How we doing? So help me out here. So this is what the picture looks like. And it's symmetric. It was actually perfectly symmetric because of this. 50%. So it was perfectly symmetric. Hopefully that makes some sense. Now help me out. So the mean here, of course, was 7. So there's room. So this is like 1, 2, 3, 4, 5, 6, 7. There's room for it to go up and come back down. All right, stay with me. So what if n was 20, but p was 0.05? What's the mean then? You can do it. What's the mean? Beautiful little formula.
1.
1, I love it. The mean would be 1. Which makes sense. The 5% chance of something happening, I take 20 people, I'd expect one of them to do this thing. Because it's a very low chance. Are you guys with that so far? So what would the picture look like? Here's 0, here's 1, here's 2. It would start off, it would probably look, let me move 0 a little bit. It would look something like this maybe. 0, 1, 2, 3, 4. Does that look normal? No, it doesn't have room to grow and then shrink. So the whole idea that the mean can't be close to 0. Does that make sense? If the mean was really close to 0, it would look like that. That's freaking not normal. So does it make sense the mean has to be some amount bigger than 0? It's got to be away from that wall, so there's room for it to go up. Does that make some sense? So here's the shortcut. And then the same thing, if the mean was too big, it would run into the other wall. It's kind of the same problem. So here's the shortcut. And I think I remember telling you, I would tell you eventually a technical way to figure out if a binomial distribution is normal enough. So this is how you check. The check for normality. If the NP is bigger than 5, and the NQ is bigger than 5. I can't remember this book. Some books say greater than or equal to, but we'll just say greater than. Then it's normal enough. So that's the mean is bigger than 5, so it's far enough away from 0. This guy controls the other side. If he's bigger than 5, then it's far enough away from the other wall, so there's room for it to go up and room for it to come back down, so it can be normal. So if I have an NPQ problem, when can I say it's normal enough when these are true? This is going to become very important when we get into chapter 8, chapter 9. This will come back. So the real thing that I didn't have time to get to, this thing that I normally would call the NAB, so I don't have to say normal approximation to the binomial distribution all the damn time, right? Would be pretending like this picture is actually continuous. And then I can use z-scores. Instead of having to do like the formula 58 million times, I could just get z-scores. Because if it's normal enough, that means I can use a z-score chart, right? So that's the thing we didn't have time for. So don't think that you're supposed to understand a damn thing about this from what I just said. I'm just telling you what we didn't have time for. So you should not understand this at all. But do you understand the idea of it? If it's normal enough, what should I be able to use to get probabilities? The z-score chart. So I could actually make z-scores out of these x values. So if it's the probability that I get more than 7 successes, well, I don't want to do all that work. I can just change this to a z-score if it's normal enough. So a little more to it than that, but that's basically all we have to know for now. Yeah?
So is this part going to be on the test? Or?
No. I need to... This part will be. Just like on the practice test. Because this becomes very important. This is the most important part out of this whole thing, to be honest, is how to check when a binomial distribution is normal enough. And why is that so important? Because if it is, I've got all the answers on that chart. I just got to look at them.
So on the practice test, in the case of 5.2b,
Yes.
not normal then, correct? Because 24 times 0.12.
Careful. 5.2, part 2, I'm taking 356 people.
Oh, right.
Yeah, good. So it does turn out to be normal enough, yeah. I like it. That's the most important thing to get from what I'm saying up here. And I appreciate the reaction to whenever a teacher says, no, this won't be in the test. You guys go, what the hell are we talking about? Because more than just the freaking test is important in life. It's good to know this thing exists if this ever comes up to you in the future. But this is what I said before. Every time we have a new distribution, I want to try to see, is there a way for me to tell if it's normal enough? Well, this is how we tell if a binomial is normal enough. This is how we do it. This is how. Yes?
Can we compare that to our formula sheet?
No, this is not a formula. This is an idea. Yeah, I like it. So this you must know. So I'll say it exactly like I said. I said check NP and NQ for normality. So you just got to see if they're both bigger than 5. That's all I got to do. And then you say, yes, it looks normal enough. Okay, maybe. So that's that little side note there. And again, 85 and 86 then, if you want to do them, I'll make them extra credit. Right, if you've already done them and tried something and followed some examples in the book, I'll see if you got it right enough to get some extra credit. Right? Okay, cool. I like it. So coming back to stuff that will actually be on the test. Any questions? Any more questions? You want to do some example problems? You just want the answer key? Give me the freaking answer key, Jeff. Is that what it is? All right, let me give you the answer key. I'm going to lose some people, but oh well.